Hey class, welcome back. This is the last lecture for chapter 10. And in the first lecture we covered Lewis structures. And in the second lecture we covered electronegativity. And we also covered translating the Lewis structure into the molecules or compounds 3D geometry. Sorry, I stopped for a second because I thought I heard my kid crying. And so that's really important for us. Predicting 3D geometry is extraordinarily important for us as chemists because if we can predict the 3D geometry of a molecule, we can then also predict its chemical properties and physical properties and chemical properties. And one of those properties that we can talk about is polarity, okay? And polarity, essentially electronegativity, which leads to polarity, is essentially why oil and water doesn't mix, okay? And that's a really important thing to know, that oil and water don't mix. That can have, the fact that you know that has so many consequences in your everyday life, all right? And we'll talk about some in a little bit. So, okay, so if you combine oil and water in a container, they separate completely into distinct regions. Like there is no mixing whatsoever. And why is that? And there's obviously something about how the water molecules interact versus how the oil water interacts and how those interactions are not compatible. Okay? So something about water molecules causes them to bunch together into one region, expelling the oil molecules into a completely separate region, right? There's something about these guys on a molecular level that makes them not compatible, so they don't mix. So what is that? And does that have anything to do with its 3D structure? And the answer is yes. So remember, we've always talked about water before. I've brought it up to you several times, and this is so I'm kind of breeze past this a little bit, but just because I've said it so much, right? We know, well, actually I'll zoom up. We know that water has this bent shape, right? And we got the bent shape from the Lewis structure, all right? This is the Lewis structure right here. Around the central atom, which is water, which is oxygen, it has 4 electron groups, which places it in the tetrahedral category. All right? Tetrahedral category. Then we can sit back and say 2 of those groups are lone pairs. So that means that the molecule is bent. The 3D structure, that's the molecular structure of it. The 3D structure is bent because 2 of the lone pairs, there are 2 lone pairs within the tetrahedral electron geometry. So this is what it looks like right here. And the bond angles between these guys, right, are going to be around 109.5. For you guys, it's okay for you just to know that it's 109.5. A little bit less actually than 109.5 because these lone pairs push down, they repel each other and they repel the hydrogen atoms as well, and so the bond angles are going to be a little bit less than 109.5. But the big key take-home message from all of this is that since we have this bent structure and we know that water has this really unique property of the hydrogens having this pseudo plus charge, partial plus charge, and the oxygen having this partial negative charge, all right, the structure of water all around, the electron distribution is uneven within the water molecule. Why is that? That is because oxygen is more electronegative than hydrogen. Okay, since oxygen is more electronegative than hydrogen, these 2 electrons that are shared in this bond aren't shared equally. So the electron density spends more time around oxygen. And so what happens is that because oxygen is electronegative, this bond right here is considered polar. And again, since this bond is polar, so is that bond, right? So the bonds within water between oxygen and hydrogen are polar because oxygen's more electronegative than hydrogen. The fact that oxygen's more electronegative than hydrogen results in these polar bonds. The fact that this molecule has polar bonds associated with it and has this bent shape makes a water molecule as a whole polar, meaning there's collectively an unequal distribution of electron density, okay, that arises from the bent shape and the polar bonds. The ability, and just really fast, just to make sure you remember what electronegativity is, the ability of an element to attract electrons within a covalent bond is called electronegativity. It's the atom. How greedy is the atom? Are they really greedy? If they're more greedy than the other atom, then they're going to pull electron density closer to it. They're not going to be so good at sharing, okay? Oxygen is more electronegative than hydrogen, which means that on average, the shared electrons are more likely to be found near oxygen than near the hydrogen atom. This results in the general dipole moment, okay? This is stuff I've already been over with before. And you can see here if the dots are electron density, or the probability of electron, right? You can see here clearly that there's more probability of the electron density being found near oxygen than near hydrogen. Again, this results in this pseudo or partial positive, partial negative charge, and collectively, because since there's an unequal distribution of electron density, this is what we call a dipole moment. The result of unequal sharing is a dipole moment, a separation of charge within a bond. Okay? Now, it's not a full-on separation because it's still a part of a bond, but it is a separation of charge within a bond. Right? A dipole moment is the same thing, essentially, as saying the bond is polar. The bond is polar. So polar covalent bonds, right? These are bonds this is a covalent bond that is polar due to the unequal distribution of electron density between the two atoms that make up the bond. Covalent bonds that have a dipole moment are called polar covalent bonds. The magnitude of the dipole moment and the polarity of the bond depend on the electronegativity difference between the two elements in the bond and the length of the bond. So shorter bonds or stronger bonds, and if you have a shorter bond between a big electronegativity difference between two atoms with large differences in electronegativities, that's going to be a very polar bond. For a fixed bond length, the greater the electronegativity difference, the greater the dipole moment, and the more polar the bond. So before we talked about electronegativity in terms of periodic trends, where we know electronegativity increases as we go up a column and as we go from left to right. But we can also quantify this more specifically, this concept of electronegativity. The value of electronegativity is assigned using a relative scale, which fluorine is the most electronegative element at this arbitrary number of 4. But so we're going to give it a 4, and everything below 4 is less electronegative. So Linus Pauling is a scientist, and he introduced the electronegativity scale that's going to be talked about in the next few slides. He arbitrarily set the electronegativity of fluorine to 4 and computed all other values relative to fluorine. Again, that is because fluorine is the most electronegative atom. Why is it the most electronegative atom? Well, we talked about it today a lot in our Zoom discussion section. Remember, as we go across the periodic table, right? Atomic radii. Decreases. And that's because we're adding more protons to the nucleus as we go across. And even though we're adding electrons, we're adding them to the same shell, the same principal quantum number. So for fluorine, for example, that's n equals 2, right? And fluorine has collectively, it has 9 protons associated with it inside the nucleus, right? It has a valence shell. Now this is the n equals 1, right? So this is n equals, where you have a 1s orbital with 2 electrons, okay? That's the n equals 1 shell. Right here, that's the n equals 2, right? In the n equals 2, we have a 2s and a 2p orbital. These are the amount of electrons, right? Space for 1 electron, so we have 1, 2, 3, 4, 5, 6, 7. We have space for 1 more. That's this guy right here. Okay. That's the little, actually. So the reason why fluorine is the most electronegative atom, because what we're looking at when we're looking at size versus pull of electron density, and the fact that fluorine only needs 1 more electron to complete its valence. So it's already very greedy already because it just needs 1 more electron. But fluorine's atomic radii is small compared to a lot of other elements, okay? So it has a lot of protons within the nucleus, and its size is very small, so that means the pull, the pull of electron density from the nucleus is great. Right? So when fluorine does gain that final electron, the pull on it is very strong, okay? Because it has 9 protons within the nucleus. So remember, when it gains another electron, and in a covalent bond, that electron is shared, probably with 1 other electron as well. So maybe these 2 electrons are shared, okay? And because of fluorine's size relative to the amount of protons in its nucleus, those 2 electrons that are being shared in a covalent bond are not going to be shared equally. The pull on those 2 electrons are going to be much greater, right? The greatest, in fact, out of all of the main group elements, which is why Linus Pauling set the fluorine's electronegativity to 4. So this is the electronegativity scale. Again, we left out the transition metals, so we have all the main group ones, and you can see that as we go up a group, electronegativity increases, the values increase, they get closer to 4, and as we go across a group, electronegativity also increases, with fluorine being the most electronegative atom, okay? We have the values for each atom. The numerical values of electronegativity are listed right below, and in general, if you have electronegativity difference of, I think it's about 0.4, then that bond is polar. So for example, if you have this hydrogen, right, so hydrogen is 2.1, and you want to, let's say it's hydrogen bound to, we'll say hydrogen bound to carbon. Okay, so let me just say if it's greater, if it's greater than, the difference is greater than 0.4, we have a polar bond. So let's look at a CH bond right here. Hydrogen has electronegativity of 2.1, carbon has an electronegativity of 2.5. So overall, the difference is 0.4. There are some professors that might say that this is technically a polar bond. It's not. all right? Carbon and hydrogen are not polar. This is not a polar bond because it's not greater than 0.4. It's close, right? It is 0.4, but it's not greater than. So this would be a non-polar bond. But if we look at, let's say, the difference between hydrogen and oxygen, right, where oxygen is 3.5, you can see that the difference is much greater than 0.4. And since it's greater than 0.4, it is going to be polar. So that is, if you're a numbers person, this is a way to evaluate whether or not a bond is polar. If you're not a numbers person and you're okay with just using the trend, the periodic trend, you can use that as well. But it's always important to evaluate individual bonds. So if you have two elements that are the same, so Cl2 for example, okay, this is going to be nonpolar, and that should make intuitive sense to you guys because there's no difference between this chlorine atom and this chlorine atom. They have the same electronegativities, they are identical, right? So since they're identical, they're not going to pull on those shared electrons any differently. This chlorine atom is not going to pull on, is not going to pull on the shared electrons in this bond any differently than this chlorine atom. Finish the Lewis structure right there. So since they are not going to pull, there's no difference in electronegativity because they're identical, this bond is considered non-polar. It's a purely covalent bond, and there's no dipole moment. The molecule is considered non-polar. There's an equal distribution of electron density because these two are they're the same thing. If you have a huge difference, right? Large electronegativity difference, as opposed, like for example, between sodium and chloride. Let's go back up and see what sodium is. Sodium is 0.9, and chloride is 3.0. So we have 0.9 and was it 3.0, I think was what I said? 3.0. So we have a difference of 2.1. That is much greater than 0.4. This is a big difference. If there is a large electronegativity difference between two elements in a bond, such as what normally occurs between a metal and a nonmetal, right? Sodium chloride, the electron is completely transferred and the bond is ionic. That's what happens. It results in ionic bond because we have complete transferring of electrons. But if we have something that's intermediate, right? So we have hydrogen and we have fluoride, right? So if we go back up, hydrogen I think was 2.1, and fluoride is 4.0. Oops. So again, this one was, 2.1. This is 2.1 and 4.0, so we're looking at 1.9. So that's not that big of a difference, right? But it is smaller than 2.1, right? So if there's an intermediate difference in electronegativity between two elements, the bond is polar. It's a polar covalent bond. In HF, the electrons are shared, but the shared electrons are more likely to be found around fluorine, so that's why fluorine looks like this, right? Right. The electronegativity difference is much greater because it has this slight negative charge associated with it, the partial negative, and we have a little bit, this is more positive, right, on hydrogen. So that's what the delta plus sign comes from, right? The pseudo positive charge. But anyway, the electron distribution is, even though those electrons are shared within the covalent bond, because the electronegativities are so different, resulting in a big difference, then that means the bond is polar. So, again, what makes a polar covalent bond if we're looking at electronegativity values? Okay? The degree of the bond polarity is a continuous function. the guidelines given here are approximate. There are always little exceptions to these types of rules, but in general, if you have an electronegativity difference that's greater or less than 0.4, we're looking at a pure covalent bond, okay? We're looking at a nonpolar bond. If you have an electronegativity difference that's intermediate, anything between 0.4 and 2.0, we're looking at something that is a polar covalent bond. If you have any difference that's greater than 2.0, any difference that's greater than 2.0, it maxes out at 3.3 because that's how the electronegativities work, then that is an ionic bond. All right? And we don't get into nonpolar polar, it's just ionic. So polar bonds, nonpolar bonds are electronegativity differences of anywhere between 0 and 0.4. Intermediate differences, 0.4 to 2.0, that's considered covalent. I would actually like to say this, 0.5, all right? And anything larger than 2.0 is an ionic bond. So how does this affect the overall, how does that plus the 3D structure affect the overall, how does that affect the way that a molecule behaves? And I'm actually going to have to stop here. This is a very short lecture. My kid just woke up, so I got to go get him. I will start back up in a little bit, and we will talk about polar covalent bonds, and we'll talk about how that affects the molecule as a whole, and then we'll be finished with chapter 11.